So this is the mass spectrometry and ionization energy assignment. First question asks to explain how a sample is ionized, and it's worth 2 marks, and you can see them written here. Atoms are bombarded with electrons from an electron gun. A negative electron is removed from the atom, forming a 1+ ion. Here is the equation where E stands for an element in the gaseous state, goes to E+, and releasing an electron. That's the first ionization equation. The next question asks why it is necessary to ionize atoms, and the reason goes that the field plates are negative and they attract the positively charged ions, so they move towards the negative field plates. The next question asks about which ions are deflected more, and what you need to do is to take into account the charge and the mass of the ion. So you get greater deflection with lighter and more highly charged ions. If you calculate mass over charge, you find the lowest number, this ion will be deflected more. So in the example of oxygen, the 16 2+, 16 divided by 2 gives you 8, will be deflected more than the 16 oxygen plus isotope. 16 over 1 equals 16, so greater deflection for the 16 2+ oxygen. Then we have 35 Cl plus versus 37 Cl plus. Again, mass divided by charge. 35 divided by 1 equals 35 is deflected more than 37 divided by 1 equals 37. The next question is about where you might find these ions on the m/z axis. So remember, the m/z axis is the x-axis and the relative intensity is the y-axis. So to work out where they would appear, you need to do mass divided by charge. So in the case of 37 Cl plus, 37 divided by 1 equals 37. And for 14N2 plus, it's 14 divided by 2 equals 7. So 37 and 7 approximately. Then you're asked to think about what you would notice about the position of on the m/z axis of the lines caused by the 2 ions 16O plus and 32S2 plus. Again, work out mass over charge. 16 divided by 1 equals 16 for the O plus, and 32 divided by 2 equals 16 for the sulfur 2+ ion, so they would have the same position because their m/z values both equal 16. The next question, a fairly simple RAM question and a very important formula for you to learn. RAM equals the sum of the relative abundance times by m/z divided by total relative abundance, and you've been given the different m/z values and their percentages. So 64.2 times 24 for the first one, plus 20.3 times 25 for the second isotope, and 15.5 times 26 for the third isotope, divided by 100 because the abundances here add up to 100 because it's out of percent. That gives you 24.5 to 1 dp, which is preferred. And you are asked to suggest which element that is. So that's magnesium because its mass is closer to that value of 24.5. And in part C, you're asked to consider why the relative atomic mass is less than 64 for copper. Well, it's because the Cu63 isotope is more abundant, so if it's more abundant, the average is going to be close to 63 than 65. Key term that, use that term abundant. Next, 3a, you are asked to determine state the block in which rubidium is found. Well, it's a group 1 element, so it is in the S block. Its electron configuration is written there. 5s1 is its last configuration because its outermost electron is in the S, as in S orbital. Don't forget it's 3d10 previous to that, not 4d10. Part C, you needed to work out the relative atomic mass of rubidium given the information. Well, 85 is 2.5 times more abundant than 87, so for every 2.5 85s, there is one 87 isotope. So 2.5 plus 1 equals 3.5. You then construct your equation, same as the equation above, so 85 MOZ times by 2.5 from there, plus 87 times by 1, divide by 3.5 because the total of 1 and 2.5 is 3.5. That goes below, that's the total relative abundance or relative intensity, gives you a value of 85.6. In 3D, you are asked to explain how the abundance of an isotope in a sample of rubidium is determined. Well, here you need to talk about the detector and how it works. Learn this. Be precise in your wording. Remember, positive ion moves towards a detector, it gains an electron. Positive ion gains an electron on reaching the detector. The induced electric current is proportional to the abundance of the isotopes. The higher the abundance of the isotope, the greater the electric current that is induced. And then in question 4, you are asked to work out the mass of the other silver isotope. So you are using the same equation as you've used before for RAM. However, you know the RAM here, you've got to work out the mass of the second isotope. So you construct an equation like this. 54 is the percentage of the first isotope, which has a relative mass of 107. Because there's only two isotopes, the other isotope must have an abundance of 46, because 100 take away 54 equals 46. A is the unknown. Simplify this. So 54 divided by 100 gives 0.54. 46 divided by 100 gives 0.46. That simplifies. Rearrange the equation. 107.9 subtract 0.45 times 107 divided by 0.46 gives you A, which is 109. It's a whole number because you cannot get a decimal point of a proton or a neutron, so it's been rounded up to the nearest whole number. The next question, 5a, asks you to write an equation including state symbols to represent the first ionization energy of nitrogen. N gas goes to N plus gas plus an electron. It forms a 1 plus charge. This is unusual because N normally forms negative charges. 3 minus is what you're aware of, but this formation does happen if you supply enough energy, and it does state the first ionization energy, and that forms positive charges, not negative charges. In B, you are asked to state and explain the general trend in the first ionization of lithium to neon. Here's my diagram to show what's going on there. So lithium to neon, the value increases when you go across the period. And why does it increase? Well, lithium's got 3 protons and neon's got 10 protons. So there's an increase in the number of protons, more attraction to those outer electrons. The second factor is that the atomic radius actually starts to decrease when you go across the period. So decreasing atomic radius across the period means that there is a stronger attraction between the positive nucleus of neon and the negative electrons on its outer shell. Next, you're asked to think about why the second ionization energy of lithium is higher than the first ionization. Again, here are my diagrams to explain this. The lithium atom has got 2 shells of electrons. The equation for the first ionization energy is written here. Here's this lithium ion. This is the second ionization equation, so that's the process that's taking place to remove that second electron. So in this ion, the electron is closer to the nucleus. That makes it more difficult to remove because it's more strongly attracted. Secondly, you are removing an electron from 1 plus charge, and that is more difficult than removing it from a neutral atom, and that requires more energy to remove it from an Li plus ion. And finally, 6a, you are asked to work out the identity of element X. It's a period 3 element, that is from sodium to argon, and there are 3 ionization energies there. There's the first, second and third ionization. You can see then there's a big jump between the third and the fourth ionization energies. What that means is there are 3 electrons in the outer shell, and that means that it is a group 3 element. The group 3 element in period 3 is aluminium. This is a much bigger number because it's in a new shell closer to the nucleus, hence much more difficult to remove. And there's a man jumping high, the big jump between different levels. And finally, identify another element in the same group as X, that is aluminium, remember X, and explain how its first ionization energy would differ from X. Well, this is the trend of groups, group ionization energies. When you go up the group, the ionization energies increase. So boron has a higher value than aluminium. Gallium, indium, and thallium, they have lower first ionization energies than aluminium. So you needed to say, state one of them, and then is it higher or lower? Look at your notes to find out why that is the trend.